In this video, we're going to go over circle quiz number 2. So in the first question over here, we have a radius and a tangent to the circle that are intersecting. And we know that when a radius and a tangent to the circle intersect, they are perpendicular, meaning that they form a 90-degree angle. So what we have here is a right triangle. We know that all radii of a circle are congruent. So if OB is 7, OA also needs to be 7 as well. So if we add 18 and 7, that's 25. We know two sides of the right triangle, and we just need to find the last side. So we can use the Pythagorean theorem to do that. 7 squared plus b squared equals to 25 squared. So we have 49 plus b squared is equal to 625. Subtracting 49 on both sides, I have b squared is equal to 576. Taking the square root of both sides, b is equal to 24. Oops, I just circled 17. b is equal to 24. Okay, in the next question, the best way to go about this question, since we're finding the length of BC, is to recognize that what we have here are two similar triangles by AA. And when we have similar triangles, we can make a proportion. So I'm just going to do side from small triangle over corresponding side from big triangle and side from small triangle over corresponding side from big triangle. I can just cross multiply and divide by 4, and I have x is equal to 12.5. Over here, I'm talking about the segment lengths formed by a tangent and a secant, the segment lengths. So if we're finding the length of PA, we're going to use our formula, whole times outside equals whole times outside. So for the tangent, the whole and the outside are both x. And for the secant, the whole is 12 and the outside part is 4. So we have x squared is equal to 48. And if you use the calculator trick to simplify your radical, radical 48 simplifies to 4 radical 3. Moving along to the next one, here we have intersecting chords, and we're talking about the segment lengths. We're finding the length of CD, and what we need to recognize here is that AB is perpendicular to CD. And when we have a diameter of a circle that's perpendicular to a chord, remember that it bisects the chord or splits it in half. So I know that whatever this half is, this half needs to be as well. Now I can use my formula, part times part equals part times part. The two parts of this chord are x and x. And the two parts of the other chord are 16 and 4. So I have x squared is equal to 64. So we have x is equal to 8. Moving along, here we have a quadrilateral inside the circle, a cyclic quadrilateral. And we know from the Edpuzzle video that you guys watched a couple of classes ago that whenever we have a cyclic quadrilateral, one of its properties are that the opposite angles are supplementary. Don't confuse that with a parallelogram, rectangle, rhombus, square. Those have opposite angles that are congruent. These have opposite angles that are supplementary because it is a cyclic quadrilateral. It is inside a circle. It is not a parallelogram. It is not a rectangle or a rhombus. It's just a regular quadrilateral inside of a circle, a cyclic quadrilateral. Over here, for number 4, we're told that AF and FB are both 5 and DC 7. Remember, when we have two tangents to a circle that come at the same point, they're equal. Same thing over here. We have two tangents to the same circle that come out of the same point, so they're equal. And over here, two tangents to the circle that come out of the same point, so they're equal. If you add 7, 7, 5, and 5, 5, 5, 5, 5, 5, 7, and 7 together, that is 34 for the perimeter. Here we have sector area. I'm going to use our proportion. Part over whole equals to part over whole. That's going to be about the areas. And that's going to be about the central angles. So we need to find the area of the sector. We don't know what it is. So the area of the sector is going to be our part. The whole is the area of the whole circle. And area of the whole circle is pi r squared. So that would be 64 pi. The central angle of the part of the sector is 60 degrees. And all of the central angles of any whole circle make 360. Now, the question does not specify to round. So when we get our answer, we're going to leave our answer in terms of pi. We're not going to type the pi button into the calculator. And then finally, dividing both sides by 360. When I do 3,840 divided by 360 in my calculator, it's a long decimal, and I'm not really sure if it has an end. So I'm going to convert it to a fraction by hitting math, enter, enter. And that converts it to a fraction in lowest form. That would be 32 over 3 pi inches squared. Remember, we measure area in square units. Okay. Over here, we know that arc DA is 56. We know that arc DB is 112. And we know the ratio of arc AC to arc CB is 3 to 1. So arc AC is the 3 part of the ratio, and arc CB is the 1 part of the ratio. Before I even start on finding the angle measurements, let me try to find these missing arcs. I know that if I take all of the arcs of a circle and put them together, I get 360 degrees. So let's do that. 56 plus 3x plus x plus 112 should make 360. So we have 56 plus 112 is 168 plus 4x is equal to 360. If I subtract 168 from 360 and then divide by 4, I have that x is equal to 48. So that means arc CB is 48 degrees. And that also means if I multiply 48 by 3, that means arc AC is 144 degrees. Now I'm all set to start finding some measurements here. So it says first, determine measure of angle CEB. That's this angle right over here. Notice this angle is formed by intersecting chords. I see that letter X. And I know when we're talking about the angles formed by intersecting chords, the angle is equal to half the sum of the intercepted arcs. So measure of angle CEB, the measure of the vertical angles, are equal to half the sum of the intercepted arcs. This vertical angle opens up to the 56-degree arc, and this vertical angle opens up to the 48-degree arc. So on my calculator, let me do 56 plus 48 divided by 2. I got 52 degrees. Moving on, measure of angle F, that's an outside angle. And we know that whenever we're finding an angle outside of the circle, it's half the difference of the intercepted arcs. And notice, inside the rays of angle F, there are two intercepted arcs. There's the larger one, AB, where the endpoints are touching of the angle. And then there's the smaller one, DB, that's also contained completely inside the angle. So measure of angle F, the outside angle, is equal to half the difference of the intercepted arcs, 144 minus 112. Okay, and moving forward, oh, that's my bad. Let's try that one more time. So angle F is opening up to A and B. So arc AB is actually the intercepted arc, the larger one for angle F. So that's not 144 like I had before. That's 144 and 48 together. So 144 and 48 together is 192. So the larger intercepted arc is 192, and the smaller one is 112. So let me fix that. 192 minus 112 divided by 2, that is 40 degrees. And finally, the last one is measure of angle DAC. That's in green. Notice how angle DAC is an inscribed angle. It has its vertex on the circle. So inscribed angles are equal to half of their intercepted arc. The intercepted arc for angle DAC would be arc DC. One of its endpoints are on D and the other is on C. Arc DC is 112 plus 48. 112 plus 48 is 160. So the measure of angle DAC, since it's an inscribed angle, is half of its intercepted arc, which would be 80 degrees. Okay, here I'm going to take my line and I'm going to solve it for y. And I can see the slope now pretty clearly. And I need the line perpendicular to this one. So remember, perpendicular lines have opposite reciprocal slopes. So the slope of the line perpendicular to the given one would be opposite signs. So instead of negative, positive, and reciprocal. So flip the fraction. That would be 2/3. So now I'm going to plug into point slope form to write the equation of the line. I'm going to plug in the y coordinate of the point that my line needs to pass through for y1, the slope for m, and the x coordinate of the point in for x1. And there we have it. Okay, so there are different ways to do this proof. We actually did this proof in class. It was on the circles packet. It was one of the early proofs that we did in the circles unit. And it's a nice one because there's many different ways to do it. So what I'm noticing, first of all, is that we're proving these two angles to be congruent, angle AOP and angle BOP. And notice how those are corresponding angles in the two triangles. So this is going to be a CPCTC proof. And I know that before I can use CPCTC, I need to first prove the triangle's congruent. Now, there's a couple of ways that you can do that. You can either do that with SSS, which is actually the way I'm going to write it up, because we know that when we have tangents that come out of the same point, they're congruent. We have reflexive, and we know that all radii of a circle are congruent. So there's SSS. Another conclusion that you could have used instead was that a radius and a tangent to the circle are perpendicular where they meet. Since they're perpendicular, we do have right angles, and all right angles are congruent to each other. Using what we had before about the tangents from the same point being congruent, and about all radii in a circle being congruent, we also have SAS. And last but not least, you could also use HL. Now, if you want to use HL, in your proof, you need to state that the triangles are right triangles. You actually need a step that says the triangles are right triangles, and this is how I know. Let me write this up. Okay, so first step is my givens. And when I write it up, I'm going to use the SSS. Actually, I'll do the HL one. Okay, so here's to where I'm talking about why these are perpendicular to each other. A radius and a tangent are perpendicular where they meet. And then from here, I can say that angle OAP and angle OBP are right angles. And that's because the perpendicular lines I mentioned before, perpendicular lines form right angles. Now, I know I'm going to use HL. I don't necessarily need to say that the right angles are congruent because congruent angles is not part of HL. For HL, you need right triangles, congruent hypotenuses, which we already proved here, and the congruent pair of legs, oops, mislabeled here, congruent hypotenuses, which we already proved here, and a congruent pair of legs, which we proved over here. All I need is to say that they're right triangles before I can use HL. So I'm going to say triangle OAP and triangle OBP are right triangles. A triangle with a right angle is a right triangle. From here, I can finish up. Triangle OAP is congruent to triangle OBP. That would be HL. And then I can prove the proof statement. And that would be with CPCTC. Now, this is a long way to do this proof. If you used SSS, it would have been a whole lot shorter. Instead of being an 8-step proof, that would have been, I'm counting 6 steps. So that would have definitely cut down on some steps. Okay, let me get my compass. And then I can do this question. I'm going to pick a point on the circle. So I just picked this point. And I'm going to measure the distance from the center of the circle to this point. I'm going to measure, make an arc to show I measured. I'm going to go over to the point. And then, without changing the distance that I just measured, I'm going to make an arc so that I intersect the circle. Then, oops, oh no. Then, I'm going to take my compass and I'm going to move over to that point. And without changing the distance that I measured before, I'm going to intersect the circle. And I'm going to keep going around. And the whole time, I am not changing the distance on my compass. It's what I measured at the beginning. And for my last one, I should end up back where I started or really close to it. I'm on the computer here. The computer is not the most accurate compass. And now I'm just going to take my 6 equally spaced points and I'm just going to connect them together. And this triangle, let's see what triangle it's talking about first. Let me highlight it in a different color. Triangle FBC. So first we have to label. So let me just label my hexagon A, B, C, D, E, and F. And it's talking about triangle FBC. So let me just highlight that triangle FBC. And this would be a right triangle. The reason for that is this angle, angle FBC, this one right over here, is an inscribed angle. And inscribed angles are half of their intercepted arcs. And the intercepted arc for this angle is half of a circle is the diameter. So that's 180 degrees. And half of 180 degrees is 90. So this is a right triangle. Circumscribed circle is where the perpendicular bisectors meet to get the circumcenter. The circumcenter is the point where the perpendicular bisectors of the sides of a triangle meet. And then you can use the circumcenter as your center to circumscribe the triangle. Some people were actually trying to inscribe the triangle. That would be using the incenter, which is where the angle bisectors meet. So let me get my compass. And we're going to do some perpendicular bisectors. Oops. Okay, I'm going to do the perpendicular bisector of side BC first. I'm just picking that side. About 3/4 of the way down the line segment. The exact distance doesn't matter. And remember to use the same distance on the other endpoint. Do not change how far your compass is open. And right through those intersection points, I'm going to draw a perpendicular bisector. I got to do it for one more side. I'm just going to do side AB, doesn't matter. So I'm going over to one endpoint, about 3/4 of the way down. The exact distance doesn't matter. And I'm going to make a big arc that goes above and below. Then I'm going to move my compass over to the other endpoint without changing the distance on my compass. And I'm going to make the same exact arc. Through those intersection points, I'm going to draw my perpendicular bisector. So the circumcenter is where the perpendicular bisectors meet. To be super accurate, we could do another one, another perpendicular bisector of the last side, but 2 is enough to see where they intersect. So now that's the circumcenter, the point where the perpendicular bisectors meet. And the cool thing about the circumcenter, about this triangle center, is that if you put your compass on that center and you just open up to one of the vertices, it doesn't matter which one, I'll just open up to C, and you make a circle, it should completely enclose the circle. It should circumscribe the circle. So that's the cool thing about the circumcenter.